we went back to our definition of y equals x plus 1, to find the other variable. So there were a lot of ideas in here that I'm just introducing now. So I don't expect anybody to be able to reproduce this at this stage. But this question involves a lot of what we're going to be doing for the rest of the course, solving word problems using algebra. So all of these steps that we've done are the same steps you're going to be doing to solve many of the problems that we're going to be doing together. So you might get some practice in this chapter, the end of the chapter. That was challenge problem 2.57. So that was from chapter 2, one of the challenge problems there. So the challenge problems are definitely a lot more challenging, as you'd expect, than the rest of the chapter exercises. Cool. So I thought it was important to do that before moving on, because that sort of, has us using a lot of what we've been talking about, distributive property and the exponent rules. I want to switch gears now for the rest of the class. I want to talk about something completely different, and that's in chapter 3 here. Chapter 3 is all about number theory. And number theory involves the ideas of multiples and divisors. It's going to be really important in solving word problems. So multiples. So the idea of a multiple so A and B are numbers. A and B are numbers. A is a multiple of B if A equals B times some integer. So what that means is A is equal to B times n. And n can be any integer we want. N could be 1, 2, 3, 4, 5, 6, 7, all the way up to however big a number we want. Or a negative number. So we could say that negative 12 is a multiple of 4, because we can write negative 12 as a product of 4 times negative 3. Okay. We also say that A is a multiple of B if A can be divided by B with 0 remainder. So if 7 divided by 4, it's not going to go in evenly. You could say 7 divided by 4 is equal to 1 with remainder 3. So 7 is not a multiple of 4. So you're probably already very familiar with this, having used numbers in your math classes, knowing which numbers are multiples of which. So if you cannot divide a number evenly into a larger number, then the larger number is not a multiple of the smaller number. So if we have both 147 and 357 are, I'm going to stop trying to write so fast, are multiples of 7. Both multiples of 7. Is 147 plus 137 a multiple of 7? Is their sum a multiple of 7? Well, we can show whether or not it is by thinking about what they equal by writing them in terms of 7 and their multiple. So I can write 147. We know it's divisible by 7. We could do that on a calculator. We could do it using long division. 147 is equal to 21 times 7. And 357 is equal to 51 times 7. So knowing this, I'm going to write 147 plus 357. I'm going to write this as 21 times 7 plus 51 times 7. And this is helpful because I'm going to use the distributive property. Actually, I'm going to use the inverse of the distributive property. If both of these terms are some number multiplied by 7, could I not factor the 7 out and write this as 21 plus 51 all times 7? So I've taken these 7s and written them out front. So this is the inverse of the distributive property. What I just did. So the reason why this is important is I could say that this is equal to 7 times the sum of 21 and 51, which is going to be 72. And if I can show that 147 plus 357 is equal to 7 times some number, that must mean that 147 plus 357 is a multiple of 7. Can everybody see that? 147 plus 357 is equal to 7 times some integer. So therefore, 147 plus 357 is a multiple of 7. This may not seem like such a big idea, but this is important that we showed this. So if we know we have 2 multiples of a number and we add them together, we're going to get another multiple of that same number. Okay. I'm just going to save my slides here. next question is saying, suppose K is a multiple of 7. Is K plus 7 a multiple of 7?
Yes.
Okay, it probably is. Because we know we're just going to add another 7 onto it.
Yes, it is.
Right. So the way that we could show that algebraically, I mean, we can understand that intuitively, but let's show that using math. So we know that K is equal to 7 times some letter A, where A is any number, because K is a multiple of 7. So I'm going to say that K plus 7, we know that's going to be equal to 7A plus 7. And like I did before, if both of these terms are multiplied by 7, I could factor that 7 out and say this is A plus 1. 7 times A plus 1. And we know that A is an integer. I should write that here. A is some integer. So A plus 1 is also an integer. Therefore, K plus 7 is a multiple, will always be a multiple of 7. That's the way they would show that algebraically. So you may not be used to seeing things like this in terms of variables, but this is what algebra is all about, is about showing things in general. If we can write things in terms of variables, then we know they're true for all numbers. Okay. So next question here. Let's solve this one together. What number between 100 and 200 is both a perfect square and a multiple of 7? What number between 100 and 200 is both a perfect square and a multiple of 7? How could we go about solving this? We have to narrow down which numbers we're looking for here. Anybody have any idea where we could start with this?
Since there aren't many squares, we should start with squares. So
Yeah.
then 11 squared is 121. 12.
Okay.
12 squared is 144, and then 13 is 169. That's all I know.
169. And yeah, there's maybe one more. 14 squared. That would be 196. Okay.
And then
So
we know that. And then a multiple of 7. That means it can be divided by 7. So let's see which one can be divided by 7. 144 can. Let's see about the other one.
So we could say,
I think the first one can, maybe, right?
well, if we can write 121, we can write 121 as 11 squared. That's equal to 11 times 11. Is 11 divisible by any other number than itself and 1?
I think 11 is just divisible by itself.
Yeah, 11 is what they call a prime number. We can't divide 11 evenly by any of the numbers smaller than 11.
So
Except
I guess
1.
14 squared is it, because even 14 can be divided by it. So,
right, 14 times 14, that's 14 squared is 14 times 14. And we can say 14 is 2 times 7. And 2 times 7. So it's definitely divisible by 7. Because we have these factors of 7 in there. Even if we just had one factor of 7, it would be divisible by 7. None of these other numbers, 12 times 12 times 12 is 3 times 4 times 3 times 4, which we can even break down further into 3 times 2 times 2 times 3 times 2 times 2. That would be the prime factorization.
But that doesn't work.
There's no 7s in there, yeah. 13 times 13, we can't divide that up either. So 196 is both a perfect square and a multiple of 7. Okay, so we saw that by getting what's called the prime factorization. I'm actually going to write that out. We'll work with that more later on. The prime factorization. These are all the factors, are all the numbers that make up a bigger number, a large number. They're all the smallest prime numbers. They're all the prime numbers that multiply together to make a number. Okay, I'm just going to save my slide. Okay, here's a different kind of question than we've seen. What is the greatest three-digit number that is a multiple of 13? What is the greatest three-digit number that is a multiple of 13? So if you think we have 3 digits, three-digit number. Where could we start with this one? What is the greatest three-digit number that is a multiple of 13? Why don't we just say, if we're trying to narrow down our search here, well, we got to start somewhere. Why don't we just say, what is the greatest three-digit number? Is there a largest three-digit number? What's the biggest three-digit number that we can make? Is 100 the largest three-digit number? Is there a three-digit number that's larger than 100? Are there any numbers larger than 100 that have three digits?
Let's see. What three-digit number that is a multiple of 13? Isn't that just the square of 13 because that's greater than 100 and it has three digits?
Okay, 13 squared, that would be 169.
I think that's just one.
Is that the largest three-digit number?
It is totally not the largest. What about another 13? I guess it'll start going into the thousands if we add another 13, right?
Right. Yeah, we couldn't multiply this by another 13.
What about 13 times 10 is 130 times 5 times 10. 13 times 10 is 130, and then multiplied by 7, I guess, is, let me think, 910. That's as high as I can get.
Okay, let's try to figure out what the greatest three-digit number is. Because you're in the 900s now.
999?
999.
But
That's the greatest three-digit number. So let's start out there. Let's say 999. That's as big as we can go. What's 999 divided by 13? If we did 999 divided by 13, if you did that using long division, you're going to get some decimals. You're going to get something like 76.846 ... So it doesn't go in evenly. 999 is not a multiple of 13. But we can look to this whole number and say, well, what is 76 times 13 then? We won't go all the way it won't go all the way to 999. But we can just use this as our first estimate. If we say 76 times 13, we're going to get 988. And we couldn't add another 13 because that would push us over 1,000. Would be into the 4-digit numbers then. So 988 is going to be the largest 3-digit number that is a multiple of 13. So this question is important because it's getting us to think about, it's getting us to narrow our parameters when we're searching for a number. If they're talking about the greatest, we need to say, okay, what is the largest number that fits these parameters? If it has 3 digits, well, the largest digit we can have is 9. So we'll just put 9s in all of our digits. And then we can narrow our search by saying, okay, let's pretend that 999 is divisible by 13 and see what we get as an initial estimate. And then we'll just go down to the nearest whole number, which was 76, to get our answer. So a lot of the questions in the chapter are about making these kinds of quick estimations to zero in on a specific number we're looking for. Okay, here's another question. How many integers between 2 and 1,004 are multiples of 5? How many integers between 2 and 1,004 are multiples of 5? So we don't really want to count all of these. We can hopefully come up with some sort of systematic way of counting them. What's the first multiple of 5 after 2?
5.
5 will be. Exactly. So we could say, we know 5 is, what's the next one? What's the next multiple of 5 after 5? We can just count up by 5s, right? 1 times 5 is 5. 2 times 5 is 10, right? 10 is a multiple of 5. What's the next multiple of 5?
$15.
15. So 15 is 3 times 5, right? And we can keep going. 20, but I don't want to do that all the way to 1,004. It's going to be a lot of numbers. But we can say, what are the last multiples of 5 up to 1,004? What are the highest numbers up to 1004, what's the highest number, I should say, that's a multiple of 5? That's equal to or less than 1004. Maybe we should talk about how we know that a number is a multiple of 5. How do we know if a number is a multiple of 5? If I give you a random
Because
number,
it is divisible by 5.
okay, but how do you know that a number is divisible by 5?
Because it ends in 0 or 5.
Right, we're looking for numbers that end in 0 or 5. So what are the numbers that end in 0 or 5? What are the highest ones up to 1004? What's the highest number up to 1004 that's still divisible by 5? 1000. So we know 1000 is. What's the one before that?
995.
995. Okay. So we know we're going to have this pattern. We're going to be counting up by 5s, and we've got a lot of numbers in between here. And it goes all the way up to 995 and 1000. So 1004 is not divisible by 5. 1000 is the highest. So I'm going to think, okay, how can I write these numbers in such a way that I can see what number they're multiplying by? I can factor out 5 from each of these numbers. So instead of writing 5, I'm going to write 5 times 1. And instead of writing 10, I'm going to write 5 times 2. And instead of writing 15, I'm going to write 5 times 3. And so on. And we could even write that for 995 and 1000. So 1000 is 5 times 200. And 995 then is going to be 5 times 199. So writing them this way, how many numbers can we say are multiples of 5 in this range? How many do we have? How has writing it like this helped us count all of the multiples of 5 in this range of numbers?
I have to leave right now.
Okay, thanks for coming. See you next
Bye.
week.
See you next week.
So Emma and Yukai, how has this helped us?
Because then we could just look at the last one, how many multiples it is.
We could just look at this last number here. You say, well, that's 5 times 200. Because we've been counting, if we're counting from 1, 1, 2, 3, 4, we're counting all the way up to 200. It means we must have 200 multiples of 5. There are 200 multiples of 5 between 2 and 1004. So lots of questions in this book the Art of Problem Solving pre-algebra book, are using this type of reasoning to solve these word problems, to look for certain numbers and to count the number of specific integers of some type in a range of numbers. They start out by writing part of a sequence of numbers, the beginning and the end of the sequence, and then factor each number in that sequence into a product of two numbers, so that we can better clearly count these numbers. We can more easily count them. So this is a style of question that is going to come up again and again in this book, in the end of the chapter here. So I'm just going to save these slides here. Okay. So we don't have time to get into the next section here. The next section we're going to talk about is divisibility, which is definitely obviously related to multiples. We can talk about a number as being divisible. We can say A is divisible by B if A is a multiple of B. So we can, it's kind of just a different wording meaning the same thing. So next week, we're going to continue on with this discussion. I'm going to post more questions now for you to practice with from this chapter, as well as maybe a few challenge problems from last chapter, like the first one we worked on today, which was that long algebraic equation. So that first question, if you felt a little bit overwhelmed by it, don't worry. There were a lot of ideas introduced in that we're going to be exploring in more detail together. So that's just a first hint at what we're going to be getting at in the coming weeks of this course. So thanks again for joining me. I hope everybody has a great weekend, and I'll see you next week at the same time. Oh, I'll see you on, Tuesday at the same time. So thanks, everybody.